The idea that objects from deep space, such as the interstellar comet 3I/Atlas, could play an essential role in triggering or accelerating planet formation around massive stars is beginning to reshape our understanding of how planetary systems come into existence. According to a recent study, these wandering cosmic bodies, originating far beyond the boundaries of our solar system, may provide a solution to one of the most persistent mysteries in modern astrophysics: how planets, especially giant ones the size of Jupiter or larger, manage to form under chaotic, destructive conditions that should theoretically prevent large objects from sticking together. If a hypothesis is correct, interstellar visitors like 3I/Atlas could serve as ready-made building blocks that young stars capture, allowing these objects to become the seeds around which entire planets eventually grow. This idea not only challenges previous assumptions, but also offers new insight into how planetary systems across the galaxy may evolve in ways we have yet to fully comprehend. Comet 3I/Atlas is currently journeying through our solar system, temporarily passing near the planets before it heads back out into interstellar space, never to return. It is unlike the comets that formed here billions of years ago, which orbit the sun repeatedly and are made from leftover material from the birth of our own solar system. Instead, 3I/Atlas originated somewhere far beyond our immediate stellar neighborhood, forged around a star that could be entirely different from our sun in age, size, temperature, and chemical makeup. Its presence here offers a fleeting opportunity for scientists to study material created under alien conditions. Interstellar objects are incredibly rare. Only 3 have ever been confirmed in modern observational astronomy. 1I/Oumuamua, the first unusual cigar-shaped object detected in 2017. 2I/Borisov, a comet with a more traditional appearance observed in 2019. And now 3I/Atlas. The fact that we have detected only 3 suggests 2 possibilities. Either these visitors are truly uncommon, or our instruments are only just becoming sensitive enough to detect them when they pass through our cosmic backyard. Because they are so rare, each interstellar visitor provides scientists with a unique snapshot of the conditions that existed around the star where it originally formed. The composition, trajectory, shape, and behavior of these objects can reveal clues about the early environments of distant planetary systems. They act as messengers from far-off regions of the Milky Way, carrying with them information about other star-forming environments, places we cannot observe directly with current technology. Researchers believe that studying interstellar comets may help answer fundamental questions about how widespread certain elements, molecules, and solid materials are in the galaxy. This matters because the ingredients available around a newborn star directly influence what kinds of planets can eventually form there. Some stars produce rocky planets like Earth, while others may give rise to enormous gas giants or entire systems filled with icy worlds. Understanding what these objects are made of helps scientists map the chemical diversity of the galaxy and improve models of planet formation. The most fascinating implication of the new study is the idea that interstellar objects might not simply pass through young star systems, but could occasionally be captured by their gravity. If a young star surrounded by a thick disk of gas and dust were to snag one of these objects, the interstellar visitor could act as a solid core that rapidly gathers additional material from the surrounding disk. This process could theoretically bypass the main obstacle in current planet formation models: the meter-size barrier. Traditionally, scientists believed that planets formed when small dust grains collided and stuck together, gradually building up into larger and larger bodies. However, computer simulations show that once these grains reach about a meter in size, roughly the size of a small boulder, further growth becomes extremely difficult. Instead of sticking together, these meter-sized objects tend to collide violently, bouncing apart or shattering into fragments. This destructive environment should theoretically prevent the formation of larger structures, making it difficult to explain how planet-sized bodies ever emerge in the first place. If this barrier truly existed in nature as it does in simulations, our own solar system should not exist in the form we see today. Earth, Jupiter, Saturn, and the other planets should never have grown beyond the size of boulders. Yet they clearly did. This puzzle has long bothered astronomers, leading them to propose alternative explanations such as gravitational instabilities, pebble accretion, or local clustering of dust particles. While these ideas provide partial answers, none has been universally accepted as a complete solution. The new proposal involving interstellar seeds offers a compelling and intuitive alternative. If a large, sturdy object, already several kilometers across, entered a young protoplanetary disk, its size would allow it to survive the destructive collisions that smaller objects cannot withstand. Its mass and gravity would naturally allow gas and dust to accumulate much more efficiently, allowing it to grow rapidly into a protoplanet. This possibility could also help explain how Jupiter-sized planets manage to form around stars similar to our Sun. Giant planets require dense, solid cores to attract large amounts of gas before the young star blows the gas away with intense radiation and solar winds. Without a sufficiently large initial seed, there may not be enough time for Jupiter-like planets to form. However, an interstellar visitor, already icy, solid, and significantly larger than native debris, could provide the perfect starting point. As soon as it becomes trapped within the disk, it could begin pulling in surrounding material, allowing a giant planet to form much more quickly than current models predict. The presence of interstellar objects also suggests that planetary systems may not be isolated creations. Instead, star systems could interact with each other indirectly by exchanging solid material over millions or billions of years. A star experiencing dramatic changes, explosions, gravitational disruptions, or close encounters with another star might eject comets or asteroids from its system, launching them into interstellar space. These objects could drift for millions of years before encountering another star system. This means that some planetary systems in the galaxy may have formed partly from materials created inside entirely different environments. This interstellar exchange could help spread heavy elements, organic molecules, icy materials, and even the seeds of future planets across the Milky Way. As scientists observe more of these rare deep space wanderers, they hope to refine their theories about the early conditions of star formation. Observing 3I/Atlas in particular allows astronomers to compare it with 1I/Oumuamua and 2I/Borisov, helping them determine whether interstellar objects follow common patterns or whether each is unique. The more researchers learn, the better they can understand the diversity of planetary systems. Some interstellar comets may contain more ice than those in our solar system, while others may be richer in heavy metals or carbon-based molecules. Each difference reflects the environment of its birth. Ultimately, the study proposing that interstellar objects could jumpstart planet formation provides an exciting new direction for research. If proven true, it would mean that planet formation is not merely a local process, but a galactic one, influenced by the exchange of material between many star systems. It would also mean that our own solar system may include components that originated far from home, perhaps even from a star that lived and died long before the Sun ever formed. The presence of such ancient cosmic travelers challenges our understanding of the galaxy as a static place. Instead, it reveals a vast, dynamic environment where stars, planets, and smaller objects interact in subtle yet profound ways. As technology improves, astronomers expect to detect more interstellar visitors, study them in greater detail, and unravel the complex processes that shaped the solar system and countless others. Interstellar comets like 3I/Atlas remind us that the universe is not a collection of isolated systems, but an interconnected web of cosmic ingredients constantly moving, mixing, and reshaping the planets and stars that eventually emerge.